Today we're going to be talking about Thevenin and Norton equivalent circuits with dependent sources. Patrick. Yeah, I'm like totally doing stuff. Patrick. What do you mean 11? Class meetings. This is let's look on Canvas. Exactly right. Yeah, so I think this is the 11th class meeting. Yeah. All right, so Thevenin and Norton equivalent circuits with dependent sources. So we are just going to learn by working examples. If I can get this little window thing to go away. All right, so let's take the following circuit. Where we have a 3 ohm resistor in series with a 15-volt source. That combination is in parallel with a 6 ohm resistor. And then over here, we're going to have a current-controlled current source, 1.2 ix. In parallel with that current source is going to be a 4 ohm resistor. And then here is our set of terminals, A and B, and we want to find the Thevenin and Norton equivalent circuits. In between terminals A and B with the positive polarity reference at A, and the current direction is down. All right, so the first thing that we're going to do is we are going to find VTH here. So let me copy this circuit while you guys think about how we're going to solve for VTH. Any thoughts? Yep. Fantastic question, Camden. Let's say that IX is this current. Now that that's taken care of, and thank you for that, I appreciate it. How do we solve for our Thevenin voltage? So what is our Thevenin voltage by definition? Let's start there. Open circuit voltage measured across our terminals of interest. I explicitly told you that the positive polarity terminal was going to be at node A. So this voltage right here is the Thevenin voltage that we're trying to solve for. So now that we know what we're trying to solve for, how are we going to solve for it? IX can be part of our analysis. I mean, at this point, is there any, actually, I missed the 4 ohm resistor. All right, so is there any resistor combinations or anything like that that we can do? Camden, you're shaking your head yes, but I very much believe the answer is no. Yeah. So we can't do any resistor combinations or anything like that. There's nothing to me that's jumping out screaming voltage division or current division because we don't have a voltage source connected in series with things that look like resistances. We don't have a current source in parallel with things that look like resistances. So we're probably going to wind up having to do either nodal or mesh. So do you guys have any thoughts on whether nodal or mesh, which one would be more appropriate here? So why do you say mesh?
Um, Mostly because when you look at the IFX coming from the voltage source, and it's also the other side where terminal A is, and you don't want those.
So I would argue, so right now, as it stands, we have two meshes and then we're solving for a voltage, right? So if we did mesh analysis, we would have a two equation, two unknown system, which isn't particularly difficult to solve for our mesh currents. And then we would have to have an entirely different step / analysis in order to find VTH because mesh analysis gives us the value of currents. If we were to do nodal analysis, we would have this node, this node, this node, and this node, which looks like it's going to be more difficult. However, if we choose this bottom node to be our reference node, then we know that the pink node is just 15 volts. And so we really only have a two equation, two unknown system that's going to allow us to solve for VTH directly. So it's less work to do nodal analysis here. It's a two equation, two unknown system either way, but the direct results of our nodal analysis will give us VTH, whereas mesh analysis is going to require us to do further steps in order to figure out what VTH was based on those mesh currents. Okay. So I'm going to do this as efficiently as possible and use nodal analysis. So I'm going to call this node, I'm just going to say it's Vx, and then this node up here is going to be VA. And very quickly, hopefully we can all see that our Thevenin voltage is just going to be the nodal voltage at the positive polarity terminal, which is VA, minus the nodal voltage at the negative polarity terminal, which is ground. So VTH is literally just the VA that we're going to solve for in our nodal analysis. Okay. All right, so how do we express IX in terms of our nodal voltages? So 15 volts minus Vx over 3 ohms. All right, absolutely correct. So we've got our controlling variable. We're effectively just going to not worry about a relationship for this node because we know that it's 15 volts at this point. We don't need to more formally do that. So now we can write our KCL equation at node A, or excuse me, node X. So that's going to be this current to the left, this current down, this current to the right, and this current up. The current to the left is Vx minus 15 over 3 ohms. The current down is just Vx over 3 ohms. The current to the right is going to be negative 1.2 Ix, and the current flowing up is going to be Vx minus Va over 4 ohms. writing our KCL equation at node A. Yes, thank you. I think I said 6, but wrote 3. Thank you for that, Patrick. All right, so KCL at A, we are going to have this current up and this current to the left. So the current to the left is positive 1.2 IX. And the current up is VA minus VX divided by 4 ohms. And now we have 3 equations with 3 total unknowns. So I'm going to leave this as a 3x3 system so that I don't have to do any more work. My first variable is going to be Vx, my second variable is going to be Va, and my third variable is going to be Ix in this system. So let's see if I can do this correctly on the first go. Vx, then Va, then Ix. So in my first equation, what I'm going to do is I'm going to move the Vx over 3 ohms to the left-hand side, over on the side with the Ix, so that all my variables are on one side of the equation. So my coefficient for Vx is going to be 1/3. My coefficient for Va is going to be 0. My coefficient for Ix is going to be 1. And my constant term is going to be 15 over 3, which is 5. In my second equation, my coefficient for Vx is going to be 1/3 plus 1/6 plus 1/4. My coefficient for Va is going to be negative 1/4. My coefficient for Ix is going to be negative 1.2. And my constant term is going to be 15 over 3, or 5. In my third equation, my coefficient for Vx is negative 1/4. My coefficient for Va is positive 1/4. My coefficient for Ix is 1.2, and my constant term is 0. So solving this system, I got the following results. Vx is 10 volts. Va is 2 volts. And Ix is 5/3 of an amp. Yeah. So, as I mentioned earlier, Va is our Thevenin voltage as well, and so we found VTH. Anybody have any questions, comments, or concerns about that analysis? Patrick, thank you for finding my mistake. All right, so everybody's either catching what I'm throwing or too sleepy to give a shit, so we'll move along to the next thing. So now we are going to find I Norton. Our Norton current is found by shorting out our terminals and then finding the current that flows through the short. And I said earlier in the problem statement that our reference direction for our Norton current was down, which is why I've drawn it as down. So how might we go about solving for our Norton current here? Yeah, we're solving for a current, so mesh seems completely appropriate here. So this will be our mesh current I1. Let's make this our mesh current I2. This our mesh current I3. And we can hopefully see right off the jump here that I3 is the exact same thing as I Norton. So by employing mesh analysis, we'll be able to solve for this Norton current directly without having to do any extra work. All right, so we have a current source that's on the interior of the circuit, so we are going to need a current relationship equation. So that's going to look like 1.2 Ix will be equal to I2 minus I3. Ix is just I1. We can see that by inspection. And so I am just going to substitute where I see Ix here and put I1 and get rid of an equation that is. All right, so hopefully everybody's catching what I'm throwing here. If Ix is just I1, I can very easily make that substitution. Now let's do Kirchhoff's voltage law around our super mesh. So this will be super mesh 2, 3. So it looks like it's going to be 6 ohms times I3 minus I2 plus 4 ohms times I2 is equal to 0. KVL around mesh 1, I'm going to have negative 15 volts plus 3 ohms I1 plus 6 ohms. Hold on. Here I had I3 minus I2. This should be I3 minus I1. I apologize for that mistake. 6 ohms times I1 minus I3 is equal to 0. And once again, we have 3 equations, 3 unknowns. So we'll go ahead and solve the system. So in my first equation, my coefficient for I1 is 1.2. I'm going to move the I2 and I3 from the right-hand side of the equal sign over to the left-hand side of the equal sign so that all of my variables are on the same side. So that's going to make my coefficient for I2 negative 1 and my coefficient for I3 positive 1. My constant term will be 0. In my second equation, my coefficient for I1 is negative 6. My coefficient for I2 is positive 4. And my coefficient for I3 is positive 6. My constant term is 0. In my third equation, my coefficient for I1 will be 3 plus 6 is 9. My coefficient for I2 is 0. My coefficient for I3 is negative 6. And my constant term will be positive 15. So solving this system, I wound up getting I1 as 125 over 69 amps. I2 came out to be 55 over 23. And I3 was 5 over 23. Anybody, excuse me, did anyone else get those numbers? All right, getting some thumbs up here. So looking like I've pulled my hat out of my ass with respect to typing stuff into my calculator for the day. So that's great. We know that I3 is I Norton, and so we're done with this step. So now let's talk about how we're going to find our Thevenin. So by definition, our Thevenin voltage is simply the ratio of our Thevenin resistance is the ratio of our Thevenin voltage to our Norton current. So that would be 2 volts divided by 5/23 of an amp looks like it'll be 46/5 of an ohm if I did my mental math correctly. Let's check that. 2 divided by 5/23. 46/5. Absolutely. Is there a way for us to check this? Well, let's look. So the process that we've used to this point in calculating or determining the Thevenin resistance directly was to look at a dead network, meaning that our 15-volt source would have to be turned off, and look into our terminals of interest and use resistor combination techniques. However, we have a little bit of a problem in as much as there's a dependent source here in the way. So we are going to have to think of something else. So I want you guys to recall, and this is from the third day of class, that if we excite a circuit, does not matter what the circuit is, as long as it's linear, which is the only thing we're going to be dealing with in this class. We measured the voltage drop across the terminals of the network, and we measured the current flowing into the terminals of the network. The ratio of that voltage to that current was the resistance of the network. So that's exactly what we're going to do in this case. We are going to apply a test source. And we are going to determine the quantity V test and the quantity I test. And the ratio of those two things is going to be the exact same thing as what our Thevenin resistance is. Now, I want to clarify here, we can only apply the test source method to a dead network and expect to get the right results, because we're finding the Thevenin resistance, and the Thevenin resistance is always the resistance of the dead network. So we have to make sure that we turn off all of our independent sources in order to do this, okay? So we're going to work this two ways, once with a voltage source and once with a current source. And we're going to find out that regardless of the type of test source that we choose to employ, we're going to wind up getting the same answer. So there's really no wrong way to do it, okay? So do you guys want to work this with a voltage source or a current source first? Okay, so current source first. So Camden, since you suggested current source, I would like for you to tell me the direction that our current source should have. Does not matter. You pick. Up, okay. And what value should this current source have? Also, does not matter. 1 amp, okay. So that's typically what I would choose unless I had kilo ohm size resistors, and then I would choose a milliamp or something like that so that I don't get astronomically large voltages. Okay, so what we have just done is effectively set I test to be 1 amp. So now our goal is to solve for that quantity V test. How are we going to do that? How did we solve for effectively that exact same voltage, except that that 1 amp current source wasn't there like 10 minutes ago? Nodal analysis. It was fairly easy and straightforward. So I would argue, let's take a crack at that again, right? So here's our node Vx. Here's our nodal voltage VA. This seems like it's going to be pretty straightforward. So, we don't have any voltage sources or anything like that to worry about, so we don't have any voltage relationship equations at all. Let's define ground to be down here at the bottom. So, what is IX? So if IX were flowing to the left and down through the 3 ohm resistor, that would be correct, but it's flowing in the opposite direction. So what do we need to do? Negative sign. Absolutely right. So negative Vx over 3 ohms. All right. Now we can write our KCL equation at node X. So that's going to be Vx over 3 plus Vx over 6 minus 1.2 Ix plus Vx minus Va over 4 ohms is equal to 0. Now we can write our KCL equation at node A. So that's going to look like 1.2 Ix plus Va minus Vx over 4 ohms minus 1 amp is equal to 0. And we now have a 3 equation, 3 unknown system to solve for. And we can see from the jump that VA is the same thing as V test. So let's solve this system. So I'm going to move that Vx over 3 ohms to the left-hand side so that my coefficient for Vx is going to be 1/3. My coefficient for VA is 0. My coefficient for Ix is 1. My constant term is 0. In my second equation, my coefficient for Vx is 1/3 plus 1/6 plus 1/4. My coefficient for VA is negative 1/4. My coefficient for Ix is negative 1.2. My constant term is 0. In my third equation, my coefficient for Vx is negative 1/4. My coefficient for VA is positive 1/4. My coefficient for Ix is positive 1.2. And my constant term is 1. So solving this system, I get Vx is 2 volts. VA is 46 over 5 volts. And Ix is negative 2/3 of an amp. Our Thevenin resistance is going to be V test over I test, which is 46/5 of a volt divided by 1 amp is 46/5 of an ohm. And that exactly agrees with what we found by taking the ratio of V Thevenin to I Norton. So a test current source got us the exact same results. Now let's take a crack at the same thing with a test current source, or excuse me, a test voltage source. Looks like you guys are still writing stuff down, so I'll slow down for a second. Only if you use a current source, because if you use a voltage source, it'll be the reciprocal of your resistance. But yes, which we'll see in just a moment. All right, so a third way is to apply a test current source. Let's do it here. So here's our current Ix. We're going to apply a test voltage source. And we need to be looking at a dead network. So do we want the positive polarity of our voltage source to be on top or bottom? Janae, pick one. Top? Okay. What do you want the value of that voltage source to be? 7 volts. Okay. So right from the jump, we know that V test is 7 volts. And now our goal is to solve for the quantity I test. All right, so how are we going to solve for this current? Mesh, sure. So this will be mesh current I1, I2, and I3. Once again, we have an interior current source, so we're going to need a current relationship equation. So that will be 1.2 Ix is going to be equal to I2 minus I3. Now we're going to write our KVL equation around our super mesh. So that's going to look like 6 ohms times I3 minus I1 plus 4 ohms times I2 plus 7 volts is equal to 0. KVL at mesh 1 gives us 3 ohms times I1 plus 6 ohms times I1 minus I3 is equal to 0. And we can see very easily that Ix is just I1, so I'm going to make that simple substitution up here yet again. And we're left with a 3 equation, 3 unknown system, so let's solve for it. All right, so in my first equation, my coefficient for I1 is 1.2. My coefficient for I2 will be -1 when I move it over to the same side as the other variables. My coefficient for I3 will be +1. My constant term will be 0. In my second equation, my coefficient for I1 is -6. My coefficient for I2 is +4. My coefficient for I3 is +6. And my constant term will be -7 volts. In my third equation, my coefficient for I1 will be 3 plus 6 is 9. My coefficient for I2 is 0. My coefficient for I3 is -6. And my constant term is 0. When I solve this system, I got I1 to be -35 over 69 amps. I2 came out to be -63 over 46 amps. And I3 came out to be -35 over 46 amps. Our Thevenin resistance, RTH, is our test voltage, V test, divided by our test current, I test. So V test was 7 volts. What's I test in this case? Negative I3, so that would be +35 over 46. And so 7 over 35 is going to look like 1/5, so 46 fifths of an ohm. 3 different ways, all getting the same result, which means all of our analysis to this point has been correct. It is a damn miracle. All right, so I just want to reiterate here that the test source method can only be used for finding the Thevenin resistance directly of a dead network. So on your in-class assignment, and you'll see on exam 2, a few weeks from now, I will give you problems that don't have any independent sources whatsoever. So if you have a network that only contains dependent sources and you're asked to find the Thevenin resistance, that is effectively telling you you have to use the test source method because there's no way to find the Thevenin voltage and Norton current because there's no live network, so to speak, to deal with, okay? So if you have independent sources in your system, you can find the ratio of V Thevenin to I Norton to get R Thevenin, or you can use the test source method. If there are no independent sources, your only option is the test source method. All right, I'm done. You've got an in-class assignment and a mini lab, so probably work on the mini lab first.